So let's get started. I don't think we had any homework due last night, did we not? If I remember right. And we have a quiz today over, I believe, what, section 2.2, if I remember the section numbers right. And so let's continue on. Just a little public service announcement. What is happening tonight? Big blue supermoon tonight. It's like so take some time this evening around 9:30, go out and look at the moon. Take a little study break. It's our last big supermoon, blue moon for quite a while, if I remember right. So, what's that? 2027, yeah. Thank you, Tristan. My wife told me, she was telling me about it, but it was like, I just remembered blue supermoon. So, and I was out last night. It was spectacular last night too. So, all right. So, always encourage you to get outside, get a little fresh air once in a while. So, all right. So last time in 2.4, we defined what were vertical asymptotes, and really what happened on a vertical asymptote was the function went off to what? Infinity or what? Minus infinity. And if we had this drawing, what would we say the limit as x approaches a, we'll call that function f of x. What would we say that limit is? Does not exist. And why would we say it does not exist there, Magnus? All right, and we don't know if they're exponentials, but yeah, one's going off to positive infinity, one's going to what? Negative infinity. All right, and so exponentials are actually reserved for a class of functions. So, but they look a little bit like exponential growth. All right, and what would we say the limit as x approaches a from the positive side is, and the limit as x approaches a from the negative side is? Go ahead and decide both of those for me real quick. So the positive side means what? We're coming in from positive infinity, right? And where am I going? I'm going to what? Negative infinity. So this would be what? Negative infinity. And coming in from the negative side, this would be what? Positive infinity. So we can have infinity or minus infinity for either a single-sided limit or what? A two-sided limit. The two-sided, they both have to go what? Up. And if either one of those, any one of these cases is what? Infinity or minus infinity, what did we have again? A vertical asymptote, a VA. And this was what? A vertical asymptote. And I think I misspelled asymptote, so spell it right, please. And then, so that was your true first time you actually been given a true definition of a vertical asymptote. We never could really define it in our high school algebra classes or in our college algebra classes. All right. So now we want to look at what happens when x either goes to positive infinity, x gets big, or x gets very small. So what happens when we go off to the left? What happens when we go off to the right? Okay, and let's take a function to begin with. Let's take f of x to be x over the square root of x squared plus 1. And we're going to look at this without its graph to begin with. Bear with me a second. I didn't organize my space very well this morning. All right, so we're going to look at what happens when we go out to infinity and what happens when we go out to minus infinity. So let's start with infinity. So let's look at the limit as x gets big, as x goes to infinity of this function. Okay. So there's not a lot I can do here, but I'm going to do a little factoring here. I'm going to rewrite this, the limit, as x goes to infinity of x. And then in this here, I'm going to factor out an x squared. And when I factor out an x squared from x squared, I get a 1. And here I get 1 over x squared. So I just factored out the x squared from underneath that radical there, inside the radicand. Now, technically, the definition of the square root of x squared is the absolute value of x. And the reason why is, if I square negative 2 squared, it's still 4, and what's the square root of 4? 2, which is the absolute value of negative 2. The square root always what? Puts out what? The principal root, the positive root. So as x is going to infinity, well, that means we're positive, right? And what's the absolute value of a positive number? Positive. So that means we can pull that out. We get the limit as x goes to infinity of x. I'll pull that out. It comes out as an x. I still get the square root of 1 plus 1 over x squared. Okay. Anybody see anything that will cancel? X's cancel, right? That's the whole reason I did that trick, by the way, in case you're wondering. We get the limit as x goes to infinity. X's cancel, I get 1 over 1 plus x squared. Give me a chance to get caught back up here. All right. So now, we know we have the limit laws. We know the limit laws are what? Very nice. Limit of the quotients, the quotient of the limits. We can pull out, we can do the limit underneath the radical and all that stuff. So we're not going to break it out in individual steps here. What's the limit of the numerator? 1, right? It's a constant. A little slow there, class. Let's work on that. Now here, what's the limit of this constant? 1. All right, so now, as our x gets big, I take x1 and divide it by a bigger and bigger number. Think about that for a second. So like, take 1 and divide it by 1,000 squared. 1 divided by 1,000,000 squared. What is happening to this quantity here? Going to get closer and closer to what? 0, right? You take 1 and divide it by bigger and bigger numbers. Where is this headed to? This is headed to 0. And so we're not going to try to justify that. We're going to live off of our intuition there. We'll summarize that up here in a second. And then what do we have left? Well, what's 1 plus 0, class? 1 is square root of 1? 1. What's 1 divided by 1? 1. So what does that limit look like? 1. And so we're going to start using the fact about some powers. We'll summarize that theorem there in a second. But good intuition there, Tristan. All right. So now let's look at the limit as x goes to negative infinity of that same function. So now we're going to negative infinity. So we'll do the same, start off the same steps. We're going to limit as x goes to negative infinity. I get the x. I'm going to factor out the x squared, and I get 1 plus 1 over x squared. Okay. So now we have to figure out what is going to be the square root of x squared, which I know is the absolute value of x. And right now, what do we know about our x's? They're going to negative infinity. So our x's are negative. So if my x is negative 100, how do I make a negative 100 positive? I change its sign. So what's this going to be in this case? It's going to be minus x, because if your x's are negative, what's the opposite of a negative? What's the opposite of a negative? Positive. Remember, the square roots only put out positive roots. So this case, what's going to happen? We're going to get the limit as x goes to minus infinity. We're going to get x, but this is now going to come out, but it's not going to come out as x. It's going to come out as a minus x square root of 1 plus that there. Get some space here. So that's a little trick that when we go to minus infinity, sometimes you're going to have to what? Think about making that square root be positive by changing its sign. Now what cancels? X's still cancel, but what do we have left that didn't cancel, that wasn't there before, is what? That negative. I'm going to put it up front there. Square root of 1 over 1 plus x squared. All right, go ahead and see if you can use your intuition there on that limit and see if you can come up with it. Two, 4, 6, 8, 10, 11. Definitely missing a couple right now. Caleb? Because we're going off to negative infinity. So let's recall. If I ask you, let's take negative 2 squared. What is that? That is 4, right? Or square root of 4. And what is the square root of 4? 2. Which is what? Positive. So if your x's are less than 0, and you need to make sure that they come out as positives, well, what do? Your x's are negative. How do you turn a negative into positive? You change its sign. Right? And that's a little trick we got to add into our bag of tricks on limits. When you're going to negative infinity, sometimes you're going to have a negative sign pop up like that. Okay. So let's go back and finish this. So now if I take 1 and divide it by bigger and bigger numbers, what's happening there? That's going to go to what? 0. So this is going to go to 0. And then what do we end up with? A negative 1 there. And we'll summarize some of this up as theorems here in a second. This is kind of our motivation here. And now let's look at its graph. Let's look at the graph of this function. And I'm going to go ahead and do it on my computer. I forgot to get GeoGebra open here so I can get it recorded. So let me get the GeoGebra.org. Let me start a calculator here. Morning, Mark. Hopefully you didn't get a speeding ticket. That is good. I always give my quizzes at the end of the hour, so please don't race over here. Do a Domino's thing. You're all too young to remember. Domino's used to advertise delivery in 30 minutes. Their pizza was free. What happened? One of their drivers, I don't remember, it was a carload of people, but killed some people racing to deliver that pizza free, and it was a big lawsuit. Was that? Yeah, this was before GPS. So this was like in the 80s. So they were really driving crazy. All right, and then what was it? It was the square root. What's the square root begin with? SQR, right? I haven't done a square root before. So notice I type SQR and now T, and I'm going to go ahead and hit parentheses there, and you'll see I got the square root. And what was it again? X squared plus 1. Right, and hit enter there. And now what did we say the limit was as x went to infinity? Oh, let me turn this grid off. Or let me just go major grid lines. A little better. We said as x went to infinity, what the function looked like it was going to? Went like it's going to what? 1, right? Notice it's kind of leveling off there. What we're going to have here is what's called what? A horizontal asymptote. And then as we went to minus infinity, it looks like these function values are leveling off to what? Negative 1. So let me add in those two lines here, and then we'll put in some definitions here. We'll type in y equals 1 and y equals negative 1. And you can see they approach really close, right? And these are going to be called what? Horizontal asymptotes. All right, so let's make our definition now. That was our motivating example. Definition. If the limit as x approaches either positive infinity or minus infinity, either one, of f of x equals L, then the line y equals L is a horizontal asymptote, or simply an HA. So if you go to negative infinity and it's an L, you have a horizontal asymptote going to negative infinity. If you have going to positive infinity equals L, you got a horizontal asymptote going to positive infinity. So it's possible to have what? One horizontal asymptote or what? Two horizontal asymptotes. It is not possible to have three horizontal asymptotes because we only got what? A plus infinity and a minus infinity. All right. So let's take some examples now. Let's look at the limit as x goes to infinity of 2 plus 10 over x squared. All right, copy that down. And then I just want you to use some intuition real quick and think about what's going on there. And use your intuition and see if you can come up with this limit before I talk about it. I'll give you about 30 seconds to think. All right, well, first off, what is 2? 2 is a constant. And this is a sum, right? So we know limit of a sum is what the sum of the limits. Now, we're going to not write all that out because it takes forever. If you write out every little step in math, you'll be writing War and Peace a bunch of times on your homework. So limit of a constant is what? A constant. What's the limit of 2 then? 2. Now, as I take 10 and divide it by numbers that get bigger and bigger because we're going off to what? Infinity, right? X squared gets there faster than x. So I take 10 and divide it by bigger and bigger numbers. What's happening to that ratio there? Smaller and smaller, right? You got a million kids, they're not getting much out of that $10 bill. So what's this happening? This is going to what? 0. And so what is this limit then? This limit is simply 2. What will we have? We'll have a horizontal asymptote, this graph, at what? Y equals 2. Now let's look at the limit of the same function as we go to negative infinity. Well, limit of a constant is still 2, right? Doesn't matter if we're going to negative infinity. You take 10 and divide it by a number that gets bigger and bigger, and square would make that what? A positive number, right? Negative squared is positive. So that's still what? Going to what? 2. That's still going to 0, and that limit is still what? 2. So we have a horizontal asymptote also going out to what? The negative infinity is left, positive infinity is right. So we should see it what? Leveling out to y equals 2, either below or above, or it could even cross a little bit. All right. Well, what's another interesting x value to look at? The limit as x goes to 0 of 2 plus 10 over x squared. All right, now 2 is still a constant, no problem there. Now let's do direct substitution. This is a rational function, right? 10 over x squared, that's a rational function. Polynomial over polynomial, it's just a simple little constant polynomial. Put in 0 into just this piece here. What form do we have here? Do we have 0 over 0? No, what does 0 over say again? Do some algebra. What do we have over here? 10 over 0. Well, you take 10 and start dividing it by a number closer and closer to 0. What's happening to that ratio? It's getting bigger and what? Bigger. And they're all going to go, what? Positive because of the square. So this is actually going to infinity. What's 2 plus infinity now, class? Infinity. So what is this? This is infinity. What does that say? We have a vertical asymptote at what? X equals 0. Okay, so what do I already know? I know the following. Here's 1, here's 2. I know I have a horizontal asymptote at what? Y equals 2. I know I have a vertical asymptote at what? X equals 0. And now I know my function either has to do something like this or this. Likewise over here because of the asymptotes. So I just need a foothold. I need to get 2 points on this graph, and I'd like to get 1 point to the left of 0, 1 point to the right of 0. So everybody come up with an x value to the left of 0 and x value to the right of 0. Okay. Now there's lots of good choices, but your best 2 choices are probably what? Plus and minus 1. If you picked anything else out, you're working too hard. Let's put in plus or minus 1 in this function. 2 plus 10 plus or minus 1 squared. And why did I do it all at once? Because of the square. What's 1 squared? 1. What's minus 1 squared? 1. What's 10 divided by 1? 1. 2 plus 10? 12. So we have a point minus 112, and we have a point 112. So my guess is, just based off of this little information, this graph looks something like this here. All right. And that's using what? Calculus and limits. And one of the things we like to be able to do is understand how graphs look and stuff without using technology. All right, so give everybody a chance to copy that down, and then let's look at some technology. All right, so let's look at this graphically. See if our intuition, let's see, where was GeoGebra? There it is. See if our intuition matches up. Let me turn these off. Our function, I'll call it g of x. What was it again? It was equal to 2 plus 10 divided by x squared. Let's hit enter. And let me go ahead and turn on its graph. And let me go ahead, what did we say we had for a horizontal asymptote again? We had a horizontal asymptote, what? Y equals 2. Zoom out there, and then I said I had a vertical asymptote at what? X equals 0. And does that look like what I drew there, class? It does. So we didn't need calculators, although now with calculus and technology, some of the graphs we do in this class are way beyond graphs I did when I was studying. My calc book is considerably thinner than your calculus book. I still have mine. Only math books, I only saved about 5 math books. Calculus was one of them. All right, now let's look at another function. And then we'll tie in some theories here. Let's take a look at this function here. We'll call it f. Let's look at the limit. We're just going to look at the limit. As x goes to infinity, 5 plus sine x over the square root of x. All right. So let's split this up. Sometimes it is nice to go through the steps. The limit as x goes to infinity of 5 plus the limit as x goes to infinity of sine x over the square root of x. And it's that sine function that's really messing us up. All right. I want you to do this first limit here, this limit right here for me. Find me that limit real quick. And what is that limit, Mark? What's that? I can't hear you. I heard 5, right? Limit of a constant is a constant. I heard 5. Yeah, it's a horizontal line. It's 5. I don't know what I heard, but I heard 5. All right. So now let's look at this one. Well, what's the problem with sine? Sine bounces back and forth. It can even be 0, right? Oh, so this is a problem here. So this is going to be a huge issue. So this one we might think about, oh, let's do a little, and I always got to remember, does this book call it the squeeze theorem or the sandwich theorem? I think it's the squeeze theorem in this book, right? I believe we had the squeeze theorem. Some books call it the sandwich theorem. All right, squeeze it or sandwich it, it's the same thing. So what do we always know about sine x, class? Sine x is always between -1 and what? 1. Now, I know the square root of x is always what? Positive, right? So when I divide by a positive number in inequality, do I have to flip anything? No. Remember, we still have inequalities, so we'd have to flip them. I'll divide everything by the square root of x. And remember, x is going to what? Positive infinity. If you think about the square root graph from your previous math days, the square root graph looks like what? This here. So as x is going to infinity, the square root of x is also going to infinity, right? The square root just slows it down, but it's still getting big. If I take 1 and divide it by a bigger and bigger number, where is that ratio going to, class? 0. And you take -1 and divide it by a bigger and bigger number, it's also going to 0, just from what? The negative side, not the positive side. So this is going to 0. This is going to 0. So where's the middle going? 0. So that means the limit as x goes to infinity of sine x over square root of x is also going to 0. And this becomes then what? 5 plus 0. And what's 5 plus 0 today, Mark? 5. So yeah, I knew I could get you to say 5 today. All right. So we still have that squeeze theorem with going out to infinities and minus infinities. So, okay. So now, we need a little bit more definitions, and then we need to kind of summarize some of this intuition we've been using. We've really been relying on our intuition right now. All right. Definition. And I'm going to go ahead and say this is an informal definition. If f of x becomes arbitrarily large as x becomes arbitrarily large, then we write the limit as x goes to infinity of f of x equals infinity. All right. So why is this informal? Arbitrarily large. That's not a definition, right? What is arbitrarily large? Am I arbitrarily large or am I arbitrarily small? Well, it depends on what you compare it to. If I'm a third grade math teacher, I'd be arbitrarily large compared to what my students. But if I compare it to the rock slides that happened on the main salmon this summer, I was pretty small compared to those rocks. So arbitrary is an informal term. All right. And then we could write up similar definitions. I'm not going to. We could write up what? The limit as x goes to minus infinity of f of x. It could be what? Infinity. This would mean as x gets arbitrarily small, f of x still gets what? Arbitrarily large. We could write them up for all of them, and we're not going to. All right. So just, there's one more thing on that section. Okay. So now we want to look at a class of functions, f of x equals x to the n. And these are called power functions. Okay. And let's look here. We want to look at f of x equals x to the n. And we want to look at two cases, when n is even and when n is odd. And we should also say here our n is a natural number. What are the natural numbers again? 1, 2, 3, and so forth. Okay, so let me get out some technology here, just so you can see them here. All right. So I don't want to sit there and type a bunch of functions, so I need a variable to represent the power. So I'm going to show you how to do a little bit of a slider here now. So I'm going to go ahead and introduce a variable. I'm just going to type n for our natural number. Actually, I'm going to use lowercase n and hit enter. And notice what it did here is it built a little slider. And now I'm going to go up and adjust this slider just a little bit here. Go to its settings. And I want it to go up by whole numbers. So I just got to come down here. And let me see here. I got to go to the slider, increment. If I want to go up by whole numbers, I want my increments to be what? Ones, right? 1, 2, 3. So I'm going to put a 1 in there. And I'm going to switch its minimum to 0, hit enter. And let's go up to 6. We don't need to go very far. Okay. I'll close that out. Okay, and now I'm going to type in a function. I've used f and g. I'm going to call it h of x, and it is going to be x to that variable n. Now, right now, what is that variable? 1. So I want everybody to visualize right now x to the first, y equals x. Visualize that graph for me real quick. Very good, Magnus. Everybody should know that when y equals x is what? You gotta turn it on. I don't have it. So right now you look like, why isn't anything there? Well, you notice I have it typed. You see the X there. Why haven't it showing? Because it's not what? Highlighted. Turn it on. So there's y equals x. Okay. So now let's look here. As x goes to infinity. As x goes to infinity, where's these function values going to? Infinity. As x goes to minus infinity, where are these functions value going to? Minus infinity. Okay, let's look at the odd cases. So I got to go up by what? 2, right? So I got to go to 3. Oops, I didn't want to play. I want to just drag it. So pause. Hang on. 3, 2, 3. Okay, so this is the graph of what? Y equals what? X cubed. As x goes to infinity, where are these values going to? Infinity, just getting there a lot faster than x, right? What about as x goes to minus infinity? These are always going to negative infinity. What's the next number up from 3? 5. So let me go up to 5. There's 5. As x goes to infinity, where are these going? Positive. These are going to what? Negative. Why are these always going to positive and these always going to negative? Think about the power there. It's an odd power. A positive to the odd power is what? Positive. What's a negative to the odd power? Negative. That's why these are always going negative. Now, what about an even powers? Well, what's a negative to an even? Positive, right? So let's look at the even cases, which would be what? 2. Notice they're both going to what? Positive infinity. What's our next positive number? 4, right? Or even number, excuse me. 4. Are they both going to infinity? They are. Why are they both going the same way? Because a negative to an even power is positive. A positive number to a positive even power is positive. Boy, that does not roll off the tongue there. And then let's see here. Let's go up to 6. That's our last one. And it's also what? Going to what? Positive. The only thing is, the bigger this power is, the flatter this becomes between -1 and 1. And if we went back to the other ones, the bigger that power is, I just want you to notice, right here, there's no flatness at what? Between -1 and 1. Let's go up power. Let's go up to the next odd power, 3. Notice there's what? Now a little bit of flatness. That's that between -1 and 1. When you take a number between -1 and 1 and take it to a bigger and bigger power, it actually gets smaller, right? 1/10 squared is what? 100. That's a smaller number. That's why that's happening. If we go up to 5, notice it actually looked like it got what? A little bit flatter in there. That's because between -1 and 1, those numbers get smaller to that power. So what if I just looked at, let's just look at one here. Let's look at y equals x to, I don't know, 101. I guess I'm going to go 111. And notice, let me just turn off the other one there. Notice that's so big, it almost made it look like a flat line, right? Why did it make it look like a flat line? Because this computer can't do enough sampling. I don't have it refined enough, and we're not zoomed in enough. You know, so if we look at, let's look at an even power real quick. Instead of 111, let's look at 110. And you see it shoots up really fast, but between -1 and 1 is basically really close to what? 0. Because 1/10 to 110th power is a really small number. All right, so let's summarize this now into a theorem. Okay, we'll just call it property. Property of power functions. F of x equals x to the n, where n is what? A natural number. It says this, the limit as x goes to n, oops, got to write, hang on a second, if n is even, then the limit as x goes to either positive infinity or minus infinity of that function is infinity. And how I visualize that, think of the y equals x squared graph. They both point up to what? Infinities. And then if n is odd, then the limit as x goes to positive infinity of f of x equals infinity, and the limit as x goes to negative infinity of f of x equals negative infinity. And the one graph that will help you visualize this is what? Y equals x cubed. And we know the bigger and the bigger the powers, what really happens is they grow faster, and between -1 and 1, they what? Flatten out more. That's the nature of power functions. Anybody study much with power functions in high school? Sometimes they do, sometimes they don't. We didn't do we haven't done a lot with them in college algebra in a long time, so. All right. All right, our next class, and we got a little bit more time before we'll take a break and then take that quiz. Reciprocals of power functions. So now we're looking at f of x equals x to the, 1 over x to the n, or x to the negative n. Okay. And their property is this, and we've been using it. The limit as x goes to infinity of 1 over x to the n. Well, it doesn't matter. You take 1 and divide it by bigger and bigger numbers, either going to infinity or minus infinity. That's going to be 0. Either for positive infinity or headed to negative infinity. And we won't prove that, but we'll use our intuition there. Okay. Everybody get caught up. So we've talked about x to the n, x to a power, like x cubes, x to the fifths. Anybody think of anything made up of a bunch of x to powers? Polynomials, right? So now what's the next thing we're going to take care of? The left and right hand behavior of polynomials. All right. So let's look at a polynomial functions. First off, let's introduce some notation for polynomial functions that some of you may have seen before, some of you may be rusty at. A lot of you are going on to bigger and better things. I mean, when I look at Group of Calculus 1 students, all I see is the future. I mean, you're going to be future engineers, future teachers, future scientists. I just see the future. So you should start thinking about upper level classes. So P of X for what? Polynomials. I know, sometimes I get a little soapboxy. All right. I am getting towards the end of my career, so I am getting a little sentimental too. So x to the n plus a n sub 1 x to the n minus 1 plus dot 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 plus a1x plus a naught, where n is an element of the whole numbers. Script W is the whole numbers. I'm going to tell you what the whole numbers are, 1, 2, 3, and so forth. And A naught, A1, A2, dot, 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 up to AN are elements of the real numbers. Give you a chance to get that notation written down, and you'll start seeing this for polynomials more and more as you move up your classes. W is the whole numbers. And the whole numbers are 1, 2, 3. So the numbers you first learn to count with. They're also referred to as the counting numbers. Nobody started with the, excuse me, they're not the whole numbers. Oh my goodness. Natural numbers. But it is supposed to be a whole number. So 0 should be in there. You started learning, I can't believe I messed up my set of numbers there, Caleb. You started learning with the counting numbers, which doesn't have 0. Whole numbers have 0. Nobody taught their children to start counting at 0. If you did, you're a pretty poor parent. So, all right. So, a bunch of terms added up. All right, so now let's look at the limit as x goes to either positive infinity or minus infinity of P of x. Well, we don't have a lot going on, but we do have these two new properties. So what I'm going to do here is I'm going to rewrite this, and I'm going to go ahead and do a little factoring. And what am I going to factor out? I'm going to factor out an x to the n from all of these terms of that polynomial. All right, so where did my stick? When I factor out an x to the n from that term, well, what's going to get left is what? An a sub n. Now, when I factor out 1 from here, well, I have n minus 1 of them, right? And I'm factoring out n of them. So I'm short 1, right? Well, if I'm short 1, that means I have to divide it out. So I'm actually going to end up with a sub n minus 1 over 1x. And that's to get rid of that minus 1 there. Then when I factor out the next term, what am I going to get there? I'm going to get an an minus 2 over an x squared. And that's going to go all the way down. And the last one is going to be an a naught over x to the n. Okay. Give you a chance to get caught up. So now, let's see what happens here. As x is either going to positive infinity or minus infinity. Well, that means this is a number. Pick your favorite number, 17. Take 17 divided by a number getting bigger to infinity or minus infinity. Where is this ratio going, class? 0, right? Take constant divided by a bigger and bigger number, that is going to 0. This is going to 0. All of those terms are going to 0. A sub n, that's a constant, times what? X sub n. So this becomes the limit as x goes to plus or minus infinity of a sub n x to the n. Well, what is that? That is the leading term of the polynomial. So it turns out the only thing that decides if it's going to negative infinity on the left or positive infinity on the right or left is what? The first term. None of the other terms affect that. What they affect is the twists and turns along the way. And we'll see that later on. Okay. So, what is this going to be? This is going to be, it's either going to be plus or minus infinity depending on n and the sign of a sub n. Because remember, negative will what? Flip things over the x-axis, our horizontal, our reflections we did in college algebra. Okay, give you a chance to get caught up. All right, so let's take a polynomial here. P of x is equal to minus 3x to the 6th plus 2x to the 4th plus 7x plus 1. And we want to know what is the limit as x goes to either positive infinity or minus infinity of P of x. Okay. Well, first thing is, what is this creature here? This is what a polynomial. So the only thing that matters on the polynomial, as we go to the left or right, minus infinity or positive infinity, is the leading term. So we're really looking at the limit as x goes to positive or minus infinity of minus 3x to the 6th. And now we want to decide this. All right, so first off, x to the 6th. Even power or odd power? Even. So I know it looks a lot like what? X squared. Right? Then what would the negative 3 do to x squared? It would what? Flip it over. So this would be negative 3x squared. Well, the x to the 6th is going to look something similar, except what? Grow a little faster and have a little flatter spot. Where are both these going to? Negative infinity. So we just have to look at that first term, and the two graphs you think about are what? X squared, because we all know x squared. Tristan did horns up for us there, right? He did that. That was awesome. And then cubed would be this, right? So, all right. Let's do another one. We'll call this one Q of x. It is minus 3x to the 5th plus 7x squared minus 2x plus 20. Go ahead. Evaluate me, find me the left and right hand limits without using technology. And it looks like I'll need, nope, that's the wrong class. Too many classes on the same sections right now. Give me a little longer. So I should have said find me the limit as x goes to infinity of q of x, and find me the limit as x goes to minus infinity q of x. All right. Now, why don't you stand up, go compare your answers, get a little stretch in. We'll go through this, and then we'll call it a day and take the quiz. Get a quick stretch in before the quiz. Compare your answers with your classmates. Pizza Planet, where's one of those at? Oh, Toy Story. How did I forget it? The Pizza Planet. Yeah, now I remember it. Yeah, I just was. And literally it was on something. It came up last night in our family conversation too. I can't remember. Oh, yeah. My son's girlfriend named her, she has a red Jeep and it's named after, who's the Jeep in the red Jeep? No, that's Cars. What's the red Jeep in? Cars? There's a red Jeep. What's the red Jeep in? One of those kids' animations. My son's girlfriend named her car after Mac or something. So we were talking about Toy Story last night at home and Cars and a couple other children animations. All right, let's do this one. So what am I really looking at? It's a polynomial. So I say the only thing that really matters is what? The first term. So I'm really looking at minus 3x to the fifth. So is that an even power or an odd power? Odd, right? So what's the one I always visualize? The cube, because I have the cube memorized. And then what's the negative going to do? Flip it over, right? So it's going to be this one, what? Right here. So as x goes to positive infinity, where are these going? Negative infinity. And as x goes to negative infinity, where are those going? Positive infinity. All right, so it really does help to have just some basic graphs, what? Known intuition-wise. So, and instead of using x cubed, you could also use what? Y equals x, because it's also an odd power. All right, so go ahead and clear your desk. You may use a calculator, but I do not think a calculator is even required on this quiz. Let me turn this off real quick.